Emilie. Thanks for being with us today. It's a pleasure. It's actually great to start with you because we are practically neighbors. So you're in Cambridge. I live in Ely. So I'm literally 10 miles from you. So
I send every one of my visitors to the cathedral in Ely because it is just so
there you
beautiful.
go. If I just step in my garden, I can see it. So it's an interesting place. Do you know that the cathedral is on the cover of the Division Bell, the Pink Floyd album? I don't know if you never noticed that.
No, I didn't.
Well, if you check this out, there's like two big. There's two statues. There's two big heads, and the cathedral. You can see the cathedral in the middle, in the distance. But anyway,
I wonder what their relationship with the cathedral
because
was.
they are from Cambridge. So they started at a famous pub in Cambridge at the Anchor that you might know. You know, it's
at the Anchor.
I'm sure you've been.
Yeah, of course.
If you go there, there's plenty of their photos and stuff. They used to hang up there, and I think they also performed there at the very beginning. But anyway, most of them, everybody except Gilmore, I think they're from, maybe even Gilmore, they're from Cambridge originally. Anyway, sorry, we are detouring completely. But Cambridge is I'm obviously not from here. You're neither, but
No.
this is the place I call home now. So it's actually nice to have you as an opener for Series 3 for that. Let me read a little bit. There's just a few lines of your sort of resume. It's very high level, just to ensure we get everything right. We don't want to add like wrong information, and that would be bad. Anyway, so you're currently assistant professor at University of Cambridge, but
That's
you're
right.
Canadian originally, from Quebec. Are you French?
From the French-speaking bit of Canada.
Is French your first language?
Yes, absolutely. I learned English very badly in school, and eventually, when I decided to become a scientist, I went to McGill, which is an English-speaking only university, and it sort of really forced me into becoming an English-speaking scientist. That was by design.
Interesting. Well, your English is excellent, by the way, better than mine.
Well, if you had met me 15 years ago, you would not have stayed back.
Okay, well, you traveled the world in the meantime, which is where I'd like to start. But just bear with me another 30 seconds. So you did your master's and bachelor and master's studies at Northwestern. Interestingly, that was after McGill, I suppose, and you did your PhD at Northwestern as well. When you actually started working more or less on the subject that you are still at the core of your research, and then you came to Cambridge for a postdoc. Then you took an assistant professor role at Rice and back to Cambridge. An adventurous life, and as far as I understand, you still keep some sort of position at Rice University. Am I right?
Yeah. I'm an adjunct assistant professor, so I am affiliated with the chemistry department there still.
Does it mean that you fly over and you stay part of the year down there and you do some work there?
No, I don't stay that much, and in fact, since the pandemic, I've obviously not been. I'm actually on my way tonight to go to Rice for a couple of days. Yeah, my luggage is waiting for me at the in my porch. It does mean that I do have ways to make really strong and lasting and continued collaboration with these people at Rice. I mean, this is a community that's very strong over there, and I didn't want to just leave and lose all these connections. So it's not a it's not a paid position. It's not a timed position, but it just means that I can have deeper connection.
It is interesting
with the people there,
and it's interesting and amazing. I was actually quite intrigued by your comment during your Talented 12 presentation about the importance of the community, which is not exceptionally new, but the way you said it was interesting. So I'm gonna go back there, but where I always like to start, and so I'm assuming that I got your resume right, which is a good start. Where I always want to start is going back a few years, because to understand the person, it's interesting to get to know how people got interested in science in the first place. So, what was your story?
Yeah, so it took me a while to really be interested in sort of, PhD level scientific research. So I come from a really small town, workers family. No one of my many cousins have ever been to university, and that typical story. And I started, in sort of high school and the equivalent of A levels, or the lycée that we have in Quebec. Started being sort of interested in science and interested in first of all how molecules affect bodies, like from a really pharmaceutical sort of way. I actually spent a year interning at Merck, working in the pharma industry. And that really spiked my curiosity for the power of chemical sciences, right? But I really didn't quite know sort of what kind of chemical sciences I wanted to do. And I eventually found my way into sort of the materials sort of realm, a bit by chance, really, a bit by who are the great mentors, and who do you see being your great teachers, and what research you start doing as an undergrad, and so on. And I think that that kind of steered me quite late compared to a lot of people. I'm not going to tell you, Paolo, that when I was 5 years old, I dreamt of being a professor. I didn't even know what a professor was. And it was really sort of on the, during my bachelor, which I knew I wanted to do science, so I went for chemistry and it was fine. But sort of during my bachelor and late in my bachelor, when I realized, okay, well, there are things to research, there are careers in unraveling new science in the chemical sciences, and then again, leaps and bounds into the avenue of sort of materials chemistry.
So, to be honest, there's nothing bad with that, Emilie. Most people get there somehow by chance. It's either pure chance or it's someone you meet on your path. But there are some people who actually think about becoming a professor when they are 3 years old or something. It's almost unbelievable to me, because I feel like my life has been quite random. But so there's nothing bad with that. It's what you make with the opportunity, right? Not how you develop it that matters to me. So would you say it's been purely random, or has there been any, I don't know, major figure, a mentor, or someone who you feel like has played a significant role in the sort of choice you made that took you to where you are now?
Yeah, there's been a few really key figures. Of course, my PhD advisor is probably the most, well, my two PhD advisors, in fact, have been the most key figures into getting me from, I kind of like research and I could be a researcher as doing a PhD, to I actually want to become a professor and lead a research team. And they both really inspired me in a way that, when I started PhD, I was like, I don't want to teach. I want to work in a national lab and just do my own thing. And they made me really feel like being a leader of a group is great. So this is Rick Van Dyne, who just passed a few years ago. And then Lawrence Marks, who is a Cambridge man himself, and that was my co-advisor. So they both really had, amazing leadership capabilities in very different ways, and truly looked like they enjoyed what they were doing. They enjoyed having a research group and interacting with students, and you could feel that passion. And being in a group where your leader is enjoying that leadership so much makes you think, well, actually, this does look like a wonderful way to live, not just a wonderful job, but an actually wonderful existence and a passionate existence.
Have they become role models? Is this what you try to be with your team now?
Well, I think I have my own personality that's neither of their personalities. They're both great leaders. I do things slightly differently, but yes, deep down, they're both passionate, and I'm trying to be passionate and trying to be there for my students and make them see that I really love my job. And I think that it's inspiring and important for me to do that, just like it was for them, for my mentors to do that.
And I'm sure it's not difficult because you probably really do love your job, right?
Oh yeah, I do. I mean, there are ups and downs, right? I'm not gonna lie. It's not wonderful every day. but on the whole, I think we're really lucky to have these kind of academic jobs, and in Cambridge especially, I would say.
Yeah, I'm sure it's intellectually stimulating, and as I always say to myself when I have a bad day, I'm not digging coal in a mine, right? So it could be much worse. Anyway.
Well, or you could be a mailman in Canada in the winter, like my mom was.
Of course.
On foot, which sounds...
Of course. Yeah, absolutely. Yeah. So not forgetting your origin is really very important. In your path, right, from where you started to where you are now, you really have traveled a lot. So in international experience, you actually come from a French language heritage, so even living and working in a different language and traveling the world, I'm sure I've had an influence to you as a person, right? Can you tell us a bit about that?
Yeah, I think I became really interested in seeing the way other cultures approach group dynamics, approach research dynamic, approach collaboration. Really early on when I first moved to Northwestern, and I've been seeking that, right? And one thing that I've tried to do really early on is actually go to these places. So I spent 3 months in Melbourne when I was a PhD student, and just was parked in a group there for that time, and it was just great to see. Okay, well, they do things slightly differently. They spend their tea break slightly differently, and they go to the pub differently than us, and that interaction is different, and you can learn very different things about leadership in a group, about the construction of a group this way, and about everything around the science as well, right? How it is to live in Chicago is very different than how it is to live in Houston and in London. Like, you just learn to appreciate different things, and so, as you say, I've traveled intercontinentally a lot. I go to lots of conferences, give seminars, and really do enjoy this interpersonal interaction that it brings, seeing people face to face, learning not just on the surface, but actually learning deep how an institution runs. I think made me just a better scientist. I can identify when it shouldn't be like that. We should actually do it this way. And it's just been, honestly, Paolo, it's just been truly interesting to discover just this whole new network of people and behaviors everywhere.
So what you're saying is that is the personal and professional experience that helps you thinking in a different way all the time, and helps you identifying things that work well and things that shouldn't be like they are, right? As you said, so potential areas for improvements, but also how to replicate models that really work, which is the key, right?
Yeah, I think a key advantage of having seen all these places, is understand the personal and the leadership approaches. Absolutely.
And it's one of the perks of a job in a scientific field, right? There is this true science is truly global, and it's not just something that you say. It really is. So you speak to people from all over the planet, and people tend to move around, and it's a deeply enriching experience that smart people know how to leverage, and of course you do. And then I want to link into the importance of the community that you mentioned at the beginning, because obviously in all your travels you met a lot of people, and you seem to really put a lot of effort in maintaining the connections, right? It seems obvious, right? Because science nowadays happens in a collaborative way. The best discoveries are at the interface between disciplines, right? You always need to keep an eye on potential applications and problems to solve. But I haven't quite met people speaking about the importance of the community like you do.
Yeah, I mean, you say that it seems obvious, but it takes effort, right, to have a really strong, cohesive community. And I think that, as I mentioned in my talk a bit earlier last month, that actually the plasmonics community it's probably not unique, but it's definitely special in the way that people are supportive of each other, are knowledgeable about each other, and are helping each other. And that's been truly wonderful for me, right? I can send an email to many people if I look for a postdoc. I've been hiring amazing postdocs from a group of people in the community that I really know and trust and have seen their work for the past decade. And it has been a really wonderful place to work when you know that there's this slew of potential collaborators out there, and that people have good faith and a really positive attitude to each other in the community. And I don't think that's true of all domains of research, but really in sort of the plasmonics world, I feel supported by my colleagues, and I felt supported when I started, as my career several years ago now, and I offer that support to my younger colleagues as well, and it is just a wonderful, secure place to develop a lifelong career, and it is just more rewarding to know that actually you don't have to be stressed about being scooped by XYZ and about all the things that a scientist might be stressed about, but rather you can think, hey, I have this great experiment in mind. I don't quite have the kit to do it, but I'm going to call XYZ, and I'm going to send him or her some samples, and we can start something. And this happens, Paolo, all the time. Like, I write a grant proposal. I'm like, ooh, I need someone with some fancy optical kit that I don't have. Think a bit, oh yeah, this person in California has it. Call them up. They're like, oh yeah, of course. And it's just constant. And it's great because it means that, we do a lot less duplication, and that we do, world leading science. We not me, but we as a field, we all do world leading science because we all have each other's help.
And this is how, science should be, right?
Should be, yes.
And do you think that being part of a sort of smaller community compared to many others, because I think admittedly the plasmonics community must be smaller than many others, right? Makes it easier, and then it becomes more and more.
Yeah, it's definitely smaller than solar cells, or
Yeah. So and do you think this makes it easier because it's kind of less aggressively competitive?
Yeah. I mean, it's obviously a growing community, and hopefully the initial spirit remains, right? But yeah, of course, anytime a community is small, it has a bit of a better chance to be cohesive and to not divide into sub-communities that then, I don't know, fight together, right? We don't really do that.
Yeah, but it's really interesting what you're saying, and it's something I haven't thought enough about. How the right spirit in a scientific community can really be that kick and push to keep a steady pace of progress.
And you can imagine how, as a community, we're better placed than other communities to win big grants because we're sticking together, and we can link together as collaborators rather than a community that say doesn't get along very well, and then they all compete for that same big grant. So that there's a big difference here.
It's not necessarily a zero-sum game, is it? If there's cohesiveness,
it's not.
The cake is bigger potentially. Yeah.
Absolutely.
It is really interesting. Yeah, and something that a lot of people should probably think more deeply about. But anyway, you kind of started mentioning, right? So we mentioned the word plasmonics, and it's about the time to actually start discussing about what you actually do, and giving you the challenge to explain me how that works, and without any visual aid, because this is a podcast. So it makes for a little bit extra added challenge. But anyway, so if I want to generalize brutally, your research focuses on the study of optical properties of nanomaterials, and particularly you look at the plasmonics properties of certain specific materials. Can you, first of all, am I right or am I completely off? And can you describe that better?
No, all the words are right, mostly in the correct order. So good job.
I like that.
So I'm really interested, kind of at the basis, about what kind of relationship does the structure of a nanomaterial impart to its. Well, no, okay. So let me start again. So what really at the basis, I'm interested in understanding the effect of the structure of a material on its properties, right? Because in the sort of the bulk world, it doesn't matter if you make a cube or a sphere or whatnot. It has the same materials property. But in the nano world, this starts to matter. If you make a cube of gold, it's not the same color as a sphere of gold, and so on. And so that whole field is sort of new and exciting. And there's a million people working on this general idea. But specifically, actually, we as a group look at magnesium nanoparticle as a way to interact with light. And magnesium behaves a little bit like silver and gold. So these particles have what we call plasmon resonance, or localized surface plasmon resonance. It's a bit of a mouthful, but LSPR. And these interact with light in a way that makes these particles readily able to absorb light, to scatter light, and to change the electric field of light around the particle. They're like antennas for light, essentially. And the gold and silver bit, the science behind the gold and silver has been known for a very, very long time. When I was a PhD student, we worked on gold and silver, so that's quite a while ago. And now we're looking at other metals because, well, first of all, gold and silver are rather expensive. Silver is not biocompatible. Gold is bio-inert, right? And they can't absorb light of all frequency. And so we've been looking at magnesium for the past about 4 years, and we found that it has different behavior. It's not just sort of incrementally better than gold or incrementally better than silver. It's actually just different. And we're pretty excited about this. We found that they're stable enough to use in a variety of solvents. We found ways to coat them such that they have a lifetime of a few hours in water, and they are actually plasmonic. They do this antenna for light behavior, really. And so this is the kind of stuff we've been working on. I'm sure your next question is going to be like, well, what are these particles going to do? Right?
Well, yeah, of course, one of my questions for sure. Please, yes, ask your question and give your answer. That I'm completely unnecessary here, which makes it fun.
No, completely necessary. But yeah, so plasmonics, as I said, have been known for a while, and there's a few key applications, but it's always about basically turning light into something else. Because again, if you have an antenna for light, the deal is that you're going to turn light into another form of energy, and then you're going to use that other form of energy to do something. And so there's two things that we do quite a lot of in my group. Is first, we turn that energy into a chemical energy. So we try to run a chemical reaction with this light, but now at the surface of this plasmonic particle. So we're concentrating that light energy at that surface through a variety of mechanisms I don't really want to get too much into. And then we can power a chemical reaction to actually limit our reliance on heating up chemical reactions. And this heating up is typically done with fossil fuels. So the idea is you'd be able to run a greener reaction if you actually take your energy, at least in part, by sunlight. The other thing that I'm really excited about is this idea of photothermal cancer therapy. And so that's been shown by some of my colleagues at Rice long time ago, that if you can put gold on a tumor, and you can illuminate, well, actually you can heat up locally the tumor by a few degrees, but just enough to kill it, and there you go. You've decreased the size of that tumor and hopefully killed all of it. That's great, but gold has no ways to get excreted from the body, right? It stays there, probably not that bad. But what you really want is something that completely dissolves and goes away after you're done with the treatment, and that's magnesium. If you put magnesium in an aqueous solution with the special coatings that we have, you have a few hours. And so the idea that you could treat someone, send them home, and by the time they get home, that magnesium's in their body. You need to eat magnesium every day to be healthy anyway. So this is really, I think, a big advantage of this reactivity.
Magnesium in water is eventually going to give you magnesium hydroxide and being dissolved, right?
It dissolves and it's all good, right?
Yeah, that's interesting. I have a ton of questions though, Emilie.
Yeah, go ahead.
on a number of angles, and it's all super interesting. So there was one thing that I was thinking while you were speaking, and I actually started thinking about it while I was reading some of your papers. And I am a chemist, so I've always looked at I start from the chemical reactions per se. But what you really seem to be speaking about is the way we deliver energy for making reactions happen. This is fascinating because if we think about heating a reaction, most of the energy we apply is completely wasted, because what we really need is the energy in the point where at the atomic level where the reaction is occurring, right? It's all the solvent heating up and vapors and the condensation and all the things that a chemist does day in and day out is absolutely unnecessary. So I thought that was really thought-provoking. In a way, I thought you could use your plasmonic magnesium as a sort of catalyst. But you're not reducing the barrier, you're actually applying energy, right? Am I looking at this correctly?
Yeah, that's correct. Okay, so that antenna effect gives us basically a local delivery system for that energy. We are not, with only the magnesium particle, we are indeed not changing the activation energy. But what we do for that is that then we go and decorate the surface of that particle with clusters of atoms or very small few nanometer particle of materials that are known to then decrease that activation energy and are catalysts, things like palladium, platinum, etc. And the beauty here is that we actually really don't need much of these materials because they're really only on the surface of that much larger antenna.
So what you're speaking about is kind of doping the
decorating.
Decorating, fair enough. Decorating the metal catalyst with your nanoparticles in some way, so that the energy can be delivered where the catalysis happens.
Okay, 1 second. I have an Amazon delivery guy here, which seemed to really insist on getting an answer.
Yeah, go for it.
All right. So
Amazon delivery guys in England are very persistent.
Yeah, they really do ring that bell. They don't want to come back.
They have to deliver that parcel. Definitely not. It's a lot of waste of energy, and they don't have plasmonic fuel. They have just petrol. Anyway.
All right, you were saying.
I don't remember anymore. I was saying So you're decorating basically your metal catalyst, and so you're delivering the energy. Well, basically irradiating it with light, as simple as that. Right on the catalytic center, so where the reaction
exactly happens. So we're capturing our energy from that central large plasmonic particle, and then that energy gets transferred through a variety of mechanisms, one of them being heat and other ones being electronic mechanism, to the small particles that are just at the surface of this large catalytic particle, where the catalytically active sites are. So it's really helping us choreograph chemical reactions by, as you say, sending the energy right at the right place without wasting sort of the heating of the entire environment, the entire bath around.
It is fascinating because it's a completely new paradigm, right? And I can see how this works on heterogeneous catalysis. Can you do that in homogeneous catalysis as well?
Well, it would be difficult in homogeneous catalysis, and you'd have to have a bit of a hybrid construct if you wanted to use a molecular based catalyst, but you could always graft that molecular catalyst on the surface of your magnesium nanoparticle, and then have it sort of dangle in the solvent, where it would then interact with the molecules in solution. So it's not quite homogeneous catalyst, but a supported molecule.
Well, supported homogeneous catalysts have been a thing for a while. Then people gave up because it was another cost for a very limited benefit. Was mostly trying to recover the precious metal, which is expensive.
Well, but separation is much easier when you do it that way.
Of course. No, that makes a lot of sense, and it's fascinating. Anyway, I'm gonna go to your cancer application later. Just want to stay on the physical chemical properties for a while. So obviously, I'm assuming, as it often happens, right? When you go from the macro to the micro, or a nanoscale in this case, properties change completely. And I'm assuming that controlling size and shape of your particle is the key to deliver or have them displaying specific properties or efficiency in the display of property. Is this correct?
That's absolutely correct.
So when do these nanoparticles stop being plasmonic? So how big are they?
Yeah, so we can make them between about 50 nanometer and then several microns in size. The true localized surface plasmon happen roughly for particles that are smaller than the wavelength of light. And so you're looking at sort of 500 nanometer and below type particles. When they get much larger than that, then you don't really get a pure localized mode. So it's truly nanoscale, but it spans a really quite wide range, right? The 10 nanometer particle would be plasmonic, and so is a 500 nanometer particle, and everything in between changes properties.
So it's fairly robust, so you don't need to be extremely precise to get the properties.
Well, that's not quite true. It is robust in that they will all interact with light of specific frequencies, but if you are actually looking for interaction at indeed a particular color, well, there is an ideal size for that. Or also, if you're looking for absorption across the visible spectrum, well, actually, you're just much better off having a variety of sizes, and then everything kind of absorbs. So that it is important to control these properties.
Okay. And I'm assuming that their shape is massively influenced by the nature of magnesium or whatever other metal with plasmonic properties. They tend to do orderly crystal structures.
Yeah, so they basically form crystals, right? Just like if you formed a macro scale magnesium crystal, it would have a specific shape, just like mineral shapes, right? And yes, magnesium actually forms really cool shapes. Whereas, if you look at, say, gold and silver and whatnot, they tend to form sort of cuboids and sort of truncated octahedron that almost look like spheres because their underlying crystal structure is cubic. So you expect that they're quite isotropic. Whereas magnesium is a hexagonal lattice. So there's one unique direction in its crystallography, which means that it forms crystals with one unique direction. And a simple example of that is if you make a magnesium single crystal, it will be a hexagonal plate, so sort of a pancake with a hexagonal pattern, like a cookie. Okay, and then we found that if you have crystallographic twins in there, it makes the same plate but twisted, well, not quite twisted, but folded at some angle that is determined by that twin plane. So very different shapes. And as you say, right, the shape affect the properties. And in this case, the shape affects that electric field that concentrates around these particles. And that's yet again another example of magnesium being different because it intrinsically forms different shapes than gold, silver, copper, aluminum, all the other plasmonic metals. It intrinsically forms particles with different properties that are just not achievable in the other metals.
On top of the advantages of being widely available on the planet and relatively
and biocompatible
compared to silver and gold, and biocompatible.
Yeah. On top of that, it's actually different.
Yes. So how do you make these nanoparticles? Do you start with a metal in solution as a salt, and you or you start with a sort of macroscopic?
No, so we basically do bottom up, right? So we start with a magnesium organometallic precursor, so say a dibutyl magnesium, for instance. We've done it with other ways. Okay. And then we reduce that with an electron on an electron carrier. So one of the things we use is naphthalene, which we reduce with an electron from a lithium metal. And then that gives you an electron carrier, and then that reduces your magnesium organometallic precursor to go from a magnesium that's sort of nominally 2+ to a magnesium that's basically 0, and then that aggregates into these particles and grow in crystals in solution.
No, that makes sense. And so I can see a lot of different directions here, because on one hand, obviously, you're looking at the properties and, the maybe relationship between the nanoparticles and its shape and form and size and whatever else, and its plasmonic property. On the other hand, you probably are working on the ways of making them, the ways of controlling their size and shape, but also on how to analyze the properties at the same time. So it feels multidimensional, really. Yeah. So how much of your focus is on all the different areas, or how much you leverage with other people in the community?
Well, we do collaborate quite a bit with other people in the community, but I think that the interdisciplinary realm that you just described is actually the composition of my group, right? So I try to have students not work on the same thing. So I have someone looking at trying to control the size of the particles. I have someone trying to control alloying in particles. And I have someone trying to actually do electron microscopy of them, like really advanced electron microscopy. And then someone look at sort of more optical approaches. And I think that within each of these projects, within each of these branches, and don't get me wrong, we're not able to sample them all. I don't have enough manpower in my group, but what we can do in each of them, there's always also an external collaborator or collaborators to help where we don't have expertise, and we can go get that expertise somewhere else.
How do you deal with these particles? In vitro, are you handling them in solid form, or do you always have like some sort of colloidal?
They're mostly suspended in ethanol or isopropanol. We can dry them, but we found that if we then try to resuspend them, it's just a little bit a little bit more complicated. They are stable in air. You can actually dry them as a powder, and they remain magnesium metal in air. So that's kind of good to know. But on the day-to-day basis, we have them as vials, basically.
And then, you know, and now I'm going slowly towards the areas you mentioned being passionate about, which is, you know, the sort of more therapeutic use of these for cancer treatment. Is you were mentioning a coating technology to kind of control stability. Yet another, you know, technological aspect to control and look at, right? Can you tell us a bit more about that? How do you coat them?
So you know, the reason why we need to coat them is that, you know, they form a magnesium oxide that's normally protective, but in water, this oxide, as you said earlier, turns into a hydroxide, it dissolves, and game over. The first type of technology we looked at was a silica coating, which is basically glass, right? Coating, and that's really typically done in nanotechnology as a way to protect cores, and we never really managed to get an enhancement of the stability of these particles, because that silica is often quite porous, and water molecules can go in and actually attack the magnesium. The way we found that works is using what's called polydopamine. So it basically is a polymer that is also biocompatible. So we're trying to use biocompatible materials here. And it does form a conformal shell on these particles. And if this shell is 20 nanometers or more, it gives us a few hours of stability before the particles actually dissolve and disappear. And we've actually submitted this really recently, and that was a large amount of work from one of my postdocs who had just left for a wonderful job back in Canada again. And so we've gotten to sort of where we want to be, because we don't want them to be stable forever, at least for the biological application. We just want them to be stable for the time you need to do that warming cancer cell operation, and then we want them to dissolve. So a few hours is really what we aimed for, and we got it with polydopamine.
And do this coating, polydopamine or whatever else, influence the plasmonic properties of the materials?
Yeah, they do a bit. And so obviously it changes the dielectric environment around the particle, and that shifts the plasmon a little bit. We're not too worried about that. And also another thing is that polydopamine itself has a bit of an optical absorption. And you know, if we keep it thin enough, we're still reaching the plasmonic core, but if it was enormous, then all the absorption you would get would be from the polydopamine, which is not really what you're looking for. So we have to be a bit careful with these, indeed.
Are you happy enough? You think you're there, or is there scope for investigating new coatings?
No, I think there's a lot of scope.
Looking at things in a different way.
For new coatings. I mean, this is a good start, because this is actually going to allow us to do the experiments in cancer cells and in cultures, because we know that it's stable enough and it's good enough. But yes, eventually we're probably going to want to finesse these coatings a bit more.
Do you have already any proof of concept of the approach working in vitro or in vivo?
Not with the cancer cells. This has been done with gold. There's actually the gold photothermal therapy is in phase 2 clinical trials. So this is known technology. We believe that it's going to work with magnesium. We have numerical data on this showing us that we are expecting a temperature change very comparable to that of gold, and so we really believe this is going to work. This is on the very short term horizon of our next few experiments.
It is really interesting, and the way I see forward is like a sort of completely innovative radiotherapy, right? With the radiation just being
yes,
light.
it's infrared light, which your body is mostly transparent to. And so, of course, you couldn't do a tumor that's really deep within you, but things like breast and cancer and skin and so on, that are, moderately surface. It is a really gentle way to really locally and incision-free, basically kill tumor cells.
Yeah. So the way this would work is you would inject the nanoparticles in the region of the cancer, and then you would irradiate it.
Exactly. And then you only need to reach just above 40 some degrees to actually kill neighboring cells, all the cancer cells, and then they just if they're dead, they just basically disperse and die.
Right. Well, that sounds very promising and super fascinating. How far do you think we are from something real in terms of application?
I mean, not that far. Given what I said, like gold is in clinical trials. I think there is a precedent for this kind of therapy. There is a lot of people in Cambridge working on similar sort of nano-biomedicine. And of course, any kind of medicine is takes a long time before reaching the customer, if you want. But I think that the proof of concepts in a few years, and then we'll see where that go. But 10 years, yeah.
Yeah, that 10 years in this field is nothing. It's
well,
practical.
I am.
That's really exciting.
No,
Really.
I am reassured that things start to move a bit faster in the medicine field with everything that happened with COVID. Perhaps our agencies have decided, actually, let's speed things up a bit.
Well, certainly, if there is one positive thing, is that they demonstrated that things can move at a much faster pace if there is the will, right? And the money. I am fascinated by one aspect always, but in your case particularly, because you have a couple, and particularly one super exciting application here. What really drives you? Is it the fundamental understanding and the science? Or is it more the promise to do something that can change people's life?
I think this has evolved in me, and I think that it probably will evolve through my career. At the moment, I really see that we have a lot of grounds to look at the fundamentals, but I really see myself as someone who's gonna start really at the fundamental and at the beginning of my career, and then just sort of help it move up and up and up in the technology readiness level, right? And how I can be part of larger and larger commercial impacts. And so, yeah, I envision that my focus will move along the technology of these materials. So at the moment, I'm really interested in the fundamentals, and I see where these might go. And probably if you come back and ask me in 10 years, I'm going to be like, oh yeah, Paolo, we've done the fundamentals 10 years ago. It was great. Now I'm actually, working with this startup and actually implementing these structures.
This is interesting because you seem to be the opposite of what an average person is, because when you're younger, you tend to be more idealistic and driven by big goals and big ideas, right? And when you get older, you get more pragmatic and you start enjoying the intellectual challenge more, right? You seem to think in the other way around, which is fine. I mean, there's no judgment here. There's no good or bad. But I just find it interesting. Good. That's interesting. And what's the future for you, Emilie, and your research, or even the field? Because this is plasmonic property have been known for a while, right? But the metals that have been explored are relatively limited, and maybe we know that already, and I don't. is there any other element that could potentially become of interest for these properties? Because at the moment it's like silver and gold, very expensive, group 1 metals, I don't know, feels like difficult to handle. Aluminium and magnesium.
Well, okay, there's also copper, but copper has a real oxidation problem as well, and it performed just as well as gold. So, no, I actually, in terms of elements, I think you've named them all, right? Of course, there are the group 1 metals. Sodium and potassium are supposed to be fantastic plasmonic, but as you say. This might become a little bit more challenging. They're not going to form a self-limiting surface oxide, but if you manage to coat them deliberately, right, during a top-down kind of evaporation synthesis, you might have a shot. Okay, they hold really good promise, but that's kind of it in the periodic table, because even if you mix two elements together, you roughly get a mixture of their dielectric function. Okay, there's a few exceptions, but they're very small exceptions to that rule. One of the exciting bit in the field is actually doped semiconductors. So in a semiconductor, if you put enough electrons in, you can actually have one of these plasmon resonances. They often occur in the IR, but that's great. We need plasmonic in the IR too. And what's exciting about these is that they can be tuned, right? You can actually tune the electron density. It's not like in a metal where you're kind of stuck with the electron density in the metal. Right. In semiconductors, you can tune that. So that's one of the area where the field is going. It's not obvious that they are going to be better than the metallic structures, and probably not in sort of higher energy, but they have proven to be very good IR plasmonics. So this is something that I would look out for, because they offer interesting.
So are you speaking about controlling? Are you speaking about controlling electronic properties via light?
No, so you can control their, basically by the doping, you can control the electronic density, and then that controls the localized surface plasmon resonance energy. Yeah.
Sure.
Yeah.
I understand. Interesting. So there are people in the community. There are several people. Emilie Ringe at UT Austin is doing just fantastic work. She's definitely one of the leaders in this field. There's a number of other people too, but I think that this is another example where this adds to the field, right? The metallic people have one angle, and then the semiconductor people have other knobs they can turn, and together we learn something about the fundamentals together. Of course, that makes sense. And probably you can't foresee all the potential interactions and overlaps that will happen a few years down the line. There could be some exciting new angle and path that will form until you progress with the fundamentals. You just don't know. It is interesting. Well, you have a lot of exciting things in your hands, and we are getting to the end of our chat. I could go on forever, but you probably have. Well, you have.
I have a flight to catch.
So I don't want you to miss that because of me. There's a couple of things I just wanted to explore, which I typically do at the end of every interview. You have progressed in your scientific career, moving from being an individual researcher to leading a team. You have spoken a lot about the importance of the community, and you have also mentioned members of your team. I'd just like to get a feel for how's Emilie as a team leader, and what is your role with the for the people working in your
I try to be very available to them, so I try to meet my students once a week, and just have really informal chats about what they're doing in terms of science, and as I explained to them when they join my group, it's not that I want to check on them, it's that I'm actually really interested in what they do. and as you become a team leader, you do less and less science. So I might do electron microscopy myself, once or twice a month, but I'm not at the bench like they are, and actually I'm just really interested and curious about the ideas they've had. And one of the wonderful things about Cambridge is that I can recruit some of the best students on the planet, and they really come up with amazing ideas, and we can have a discussion about how to implement these ideas. So I try to be really available to them, and I really believe in fostering a positive group dynamic. And so we have lots of group interactions. We used to have a lot of in-person social, and during COVID, we would play, electronic board games every Tuesday night together. Just because I feel like getting them an idea of this sense of supportive community, even in their own backyard, right, is really, really important. And that the students can feel like if they don't quite know how to do something, well, there'll be someone in the lab that they can ask, and that they will be supported no matter, who they are and what they do. And so we really try to be a cohesive, happy group that's really intellectually sort of curious.
It's beautiful to hear how you're trying to transfer the positives of your own experience, right?
Yeah.
It's what a good leader should always do. So congratulations for that. And yeah, we come to my typical final question, which is very, very much linked to what we just discussed. Is now that you are still very young, but of course already quite established in the community. You're winning awards, your research is very important, and you're doing exciting things. If you can stop and step back and look at your whole experience, what is the piece of advice you would give to someone younger, just starting in their career?
Yeah, I think it would be to really not hesitate to reach out to people and go talk to people. One of the things that helped me massively when I was applying for faculty positions is that I didn't fear going knocking, well, not quite knocking on doors, but emailing anyways, faculty members where I was a PhD and saying, hey, can I have a chat with you? I'm wondering about XYZ problem. And I think that a lot of people would be a bit afraid of doing that. But the reality is that, in science, most people are really interested in science. And if you call them up and tell them you want to talk about their research, they're going to be more than happy to do that. And so the advice is, to develop into a great researcher, really don't hesitate to ask other great researchers what they think of your ideas, what do you think of your approaches, and also what they do and how they got there.
Beautiful way to close our conversation, Emilie. Thank you very much for being with us.
Thanks, Paolo.
It's been an honor and a pleasure. Great way to start season 3 with you. And thank you very much. And congratulations, of course.
Thank you.